Yeah, take it, please.
Hello everyone, I'm Yunqin from University of Science and Technology of China. It's my honor to introduce our work of graph signal diffusion model for collaborative filtering. I'll organize my presentation into 4 parts: background, model, experiment, and conclusion. So, in today's era of information overload, recommender systems has become a vital means for users to filter information and find items to their interest. Collaborative filtering, or CF for short, is a key technology in this context. It aims to extract user preferences from historical feedback data, namely how users behave towards each item in the past. In recent years, more and more studies have been regarding CF as a conditional generative task of user interaction vectors. As it's shown in the figure, for each user U, our available input is a multi-hot Boolean vector indicating whether the user has ever interacted with each item in the item set. However, we think this user history as incomplete. Some of its entries are randomly masked out and considered as future interactions that we need to predict. Therefore, to invert such random mask out or drop out operator and reconstruct the complete interaction vector X, we resort to a generative model like VAE, GAN, and diffusion model to learn the distribution of X conditional on C. And then in practice, we use the learned expectation EX conditional on C as a personalized score vector for this user and rank all the items in the item set accordingly. With fast advancement of generative modeling in the field of AI, diffusion model has emerged with great potential in solving CF as a conditional generative task. For instance, a notable work in 2023 has modeled the generation process of user-item interaction metrics by iteratively adding and removing Gaussian noise, just as diffusion models for image generation always do. However, we argue that such standard diffusion process relying on Gaussian noise could have limitations when modeling implicit feedback data. First, the isotropic diffusion schedule ignores correlation among items, leaving the graphical structure of the interaction space unexplored. Also, Gaussian noise added in the forward process tend to destroy personalized information in user interaction vectors. As a result, it can be very hard to reconstruct the original vector X from the noisy Gaussian latent states. So to address the above 2 challenges, we propose graph signal diffusion model for collaborative filtering, or GIF-CF, to better model implicit feedback data. To give an intuitive explanation for our proposed graph signal diffusion, let's first consider the interaction vector X as a signal on the item-item similarity graph. Here, by the item-item similarity graph, we mean a graph consisting of all the item nodes with weighted edges. Each edge weight denotes the similarity between the 2 connected item nodes. Such graph can be easily constructed from our training data, the user-item interaction matrix. Where, under this notion of graph signal, the proposed graph signal diffusion can be understood as 2 opposite processes. A graph signal forward process that continuously smoothes interaction signals by simulating the heat equation on the graph. As heat dissipates on the graph, the signal becomes smoother and smoother and finally arrives at a steady state. As its counterpart, we have a graph signal reverse process that iteratively sharpens scores guided by the user history C and finally reconstruct the original interaction signal X. Unlike standard diffusion that perturbs useful signals into noise, our forward process itself could help predicting missing interactions by graph smoothing. Our reverse process then further enhances the preference scores via step-by-step sharpening. To sum up, we integrate the ideas of graph signal processing into diffusion model and therefore introduces beneficial inductive biases for personalized recommendation. That's basically why our method should work and perform better than standard diffusion. In the language of mathematics, our forward process corrupts a complete interaction signal X into a sequence of latent signals CT. As you can see from the equation, we obtain zt by multiplying x with a graph smoothing filter ft. The smoothing strength of ft monotonically increases, resulting in multiple levels of correction. Here, we write zt as a Gaussian distribution in order to show a better correspondence with standard diffusion, for which ft here should instead be a scalar value. In our method, we substitute it with a matrix that serves as a graph smoothing filter. All right, now for the reverse process, we aim to remove the smoothing effect brought by the forward process. This is the actual generative model from which we can sample latent signals in the reverse order, conditioned on the historical interaction signal C, to recover the complete interaction signal X. Under certain distribution assumptions, this process can be parameterized by neural networks x hat theta. We call it as a conditional denoiser. The model expressivity pretty much depends on its design. Yeah. In the training phase, our goal is to maximize the likelihood of reconstructed interactions. Using a variational inference technique as well as compatibility between metrics and vector norms, this objective can be relaxed as a combination of square errors plus constants. Therefore, we can write a very simple diffusion loss as shown in the last line. Here goes the pseudocode. The training step starts by sampling a user and randomly drop out its observed interactions to obtain a historical interaction vector C. Then, just like traditional way to train a diffusion model, we sample the time step t from a uniform distribution, corrupt x into zt, recover it via the denoiser, and take a gradient step on the unweighted square error. Our inference algorithm extends the idea of DDIM and turns out to be a fully deterministic mapping from zt to z0. At each inference step, we first compute a rough estimation of x from the denoiser x hat, and then update the latent states accordingly. The final preference scores in z0 are then used for personalized ranking and top K recommendation. So far, we have explained the main idea of our GIF-CF, but ignore a lot of technical details. I would like to add two important details to provide you a more comprehensive view of GIF-CF. The first one is our filter design. Recall that the forward process corrupts interactions with graph smoothing filters FT. In our implementation, we simply interpolate between the identity mapping I and an one-hop convolution kernel alpha A to get a sequence of smoothing filters, where alpha is a hyperparameter representing the smoothing strength at the last time step, and A is the adjacency matrix of the item-item graph. Here comes the question: how can we construct a good item-item graph? Drawing inspiration from two advanced graph signal processing baselines, we adopt an adjacency matrix A as follows. The first term propagates interactions to two hop neighbors on the user item bipartite graph, so it's able to capture the local structure. The second term serves as an ideal low-pass filter. It filters out high-frequency components in the graph spectral domain while preserving dense, high-order connectivity in the low-frequency subspace. By a weighted combination of these two terms, our filters effectively leverage prior knowledge on the graph and lays the foundation for graph signal diffusion. Another important detail is our denoiser design. Recall that the reverse process reconstructs interactions with a learnable denoiser x hat. To achieve high-quality reconstruction, we adopt a two-stage design of its architecture. In stage 1, the network makes the latent signal zt and the historical interaction signal c in the embedding space, following the common practice of matrix factorization-based recommender models. In stage 2, the network mixed the output from the stage 1, the historical interaction signal C and its smooth version AC, directly in the interaction space. By doing so, we intend to reduce the artifacts of low-rank compression brought by the previous stage. The next part shows our main experimental results. We compared the proposed model with 8 competitive baselines on 3 benchmark datasets in terms of top K recommendation performance. as the table shows, our GIF-CF significantly outperforms all the baselines on all the metrics on all the datasets, achieving the new state-of-the-art in the task of collaborative filtering. Specifically, it surpasses the representative GNN-based model like GCN, surpasses the state-of-the-art graph signal processing method BSPM, and also surpasses the recently proposed diffusion recommender model DiffRec. Another major observation is that as the sampling algorithm evolves, the quality of the latent signal ZT gradually improves. If we directly use Z capital T, Z T-1, and Z0 as preference scores, we will find that the recommendation results become progressively better. This validates the efficacy of the reverse process. That is, the reverse process is indeed leveraging the hierarchical generative capability of diffusion model. And then, to analyze the sensitivity of model performance on the diffusion schedule, we vary the number of diffusion steps T, the smoothing strength alpha, and the noise scale sigma T to see their effects. We observe that as the total steps increase, the performance improves at first. This shows that a multi-step hierarchical generative model is generally better than models with only one single latent variable. However, too many steps may lead to a performance bottleneck. We also find that both over-smoothing and under-smoothing can lead to performance degradation. Choosing an appropriate filtering strength would benefit collaborative filtering. Last but not least, we find that noise in the diffusion process consistently hinders the reconstruction of interaction signals. This aligns with our motivation of changing the corruption manner of diffusion model. We also conduct ablation studies on our denoiser architecture and find out that each branch we designed is indispensable for achieving state-of-the-art performance. The proposed denoiser effectively mixes information from the diffusion latent ZT and the condition C, contributing to the superiority of GIF-CF. To sum up, in this work, we propose a novel variant of diffusion model tailored for collaborative filtering with implicit feedback, which smoothes and sharpens graph signals by simulating the heat equation. By integrating graph signal processing into diffusion model, we introduce beneficial inductive biases for personalized recommendation and achieve state-of-the-art performance in collaborative filtering. The dataset, code, and weights are all open-sourced. In the future, one may consider designing more powerful denoising network or training strategies to accelerate convergence or enhance performance. Or on the theoretical side, it will be interesting to rethink the inductive bias of diffusion model for collaborative filtering from the perspective of score or flow-based models. I hope this work could inspire more researchers to think beyond the boundaries of conventional image diffusion models and design task-specific diffusion models with general corruption manners. By that means, we can truly unleash the potential of diffusion model in information retrieval. That's all for my presentation. Thank you for listening.